made the number of turns on the primary side of the transformer is equal to the number of turns on the secondary side, that is given by N2 dash. So when you make the number of turns on the secondary side equivalent to the number of turns on the primary side, the induced EMF on the secondary side will be equal to the induced EMF on the primary side. So once you have such a thing, then there is no voltage difference between these terminals. Let's consider that this is terminal A and B, and there is no voltage difference between this terminal A, B, and CD. Okay, this A and C are at the same potential, and this B and D are at the same potential. So when they both are at the same potential, you can remove this component. That is the idea behind it. So once we made N2 as equivalent to N1, the EMF induced on the secondary side is made equivalent to the primary side. So because of that, we are going to remove this component. Okay, because the potential at this terminal, that is A and B, and the potential at this terminal C and D are same. So since it is same, we are going to remove this terminal. So once we are changing the EMF induced across this terminal, what happens is the current flowing through the secondary terminal also changes. So if the secondary terminal current also changes, then the copper loss which is going to happen in the secondary terminals are going to change. But we are doing some modification. So our basic necessity is before the modification, there is some loss in the system. Thus, that loss should be maintained constant after the modification also. Okay, then only the electrical changes are not happening. The copper loss before and after the modification should be same. Then only you will be making the equivalent circuit properly. Okay, so just like that, we cannot change this circuit. We are changing the circuit by keeping the loss as constant. So once you want to keep the loss as constant, the resistance and the reactance also need to be changed appropriately in order to keep the loss as constant. So once you want to keep the loss as constant, what do we need to do? We have to equate before modification what is the power loss, and after modification what is the power loss. So let's say that before the modification, the power loss is given by I2 square into R2. Then after the modification, let's say that the current is given by I2 dash square into R2 dash. So this is before modification and this is after modification. Okay, so we do not know this R2 dash value. So we are able to find out the value of I2 dash. So I2 square divided by I2 dash square into R2 is given by R2 dash. So this is nothing but transformation ratio relation. Okay, so once you have this, then you can substitute the transformation relation for this. So then this will be like A square into R2 is equal to R2 dash. So how we have obtained this equation? We have obtained this equation based on our necessity that before and after the modification of the equivalent circuit, we wanted to maintain the losses as constant. That's why we have obtained R2 dash. So similarly, for reactance, if we calculate, we will be getting A square into X2 is equal to X2 dash. So that's why we have got R2 dash here and X2 dash here. And when it comes to the load, the load power before and after should be same. Okay, the load power before and after the modification should be same. So accordingly, we are going to keep this V2 dash appropriately. Okay, so in the load end, we are going to maintain the power constant. So V2 into I2 is the actual power before the modification. That is before we got E2 dash here, we got V2 into I2. After the modification, we got the power as V2 dash into I2 dash. Okay, so now for V2 dash, we can obtain from this relation V2 into I2 divided by I2 dash. So you understand that the power before and after the modification remains the constant. So if you keep the power as constant, then we will be getting all the relations. So accordingly, we can keep the parameters of this equivalent circuit of the transformer. Okay, so now we can see here that the relation whichever we have discussed, that is given here. Okay, so all the explanations whatever I have told you are available here. So here they have equated power. So once they have equated power, we will be getting I2 dash from the power. This is before the this is after the modification, and this is before the modification. So you can understand clearly that before the modification, if E2 is lesser, and in the after the modification, if the E2 is greater, then obviously the I2 should have been more here and I2 dash will be less here. Okay, so you understand clearly that for a constant power, when you want to do the modification on the secondary, this is on the secondary terminal itself. When you had E2, you had one current, that is I2. So now when you have E2 dash, when you are having E2 dash, that is the induced EMF on the secondary side, you are going to have I2 dash. Now the power which is given by this E2 I2 will be equal to the power given by the E2 dash I2 dash. Now when the E2 dash is increased from E2, when E2 is increased from E2, then obviously, so initially the E2 is lesser and E2 dash is higher. So in that case, our current should be reduced on here and current should be increased on here. So this is before modification, and here it is after modification. Here the current voltage is less and the current is more. Here the voltage is higher and current is lesser. So here what we have done, we have done power balance before and after the modification. From that we have obtained this relation. Okay, so already we have seen E1 divided by E2 is equal to A, E1 divided by E2 is equal to A. So that we have substituted here. So from that we have obtained this 1 divided by A, we have obtained from this equation. Okay, how we have got is this E2 dash is nothing but A into E1. So already E1 by E2 is A. Then here you are getting E2 by E1. So from that you are getting 1 by A. Okay, so that we have substituted here. So similarly from the copper loss, we have obtained this relation. So R2 dash is given by A square into R2. So you can understand clearly that the voltage E2 and E2 dash, I2 and I2 dash are related by the term of ratio of transformation A, whereas the reactance and the resistance are related by the term A square. Okay, voltage and current is related by the transformation ratio A. Reactance and resistance are related by the transformation ratio A square. Okay, you can see here the reactance X2 dash is equal to A square into X2. So here, as I said before, here they have used same kVA thing, that is mainly power. They have related the power, nothing else. Okay, so till now whatever we have seen is exact equivalent circuit. Now we will be seeing about approximate equivalent circuit. Here from the exact equivalent circuit to approximate equivalent circuit, the shunt element which was there here, the shunt element which were there here, just a minute. Okay, we'll go back to the circuit. So this is the actual equivalent circuit. In the actual equivalent circuit, you are having resistance on one side and this reactance on one side. Similarly, here resistance on one side and reactance on one side. So this is the primary part side and this is the secondary part side. Here, this is the shunt element. The current flowing through the shunt element is very much lesser. So if there is a potential across this source, let's say Vs, the potential across the source, that is Vs, that will be almost equal to the voltage across this shunt element, that is E1. Why? Because the voltage drop across the series element will be very much lesser, because the current difference is only Im. Okay, the current difference is only Im. So the voltage drop across this element will be very much lesser. So since the voltage drop across this element is very much lesser, we can approximately consider that Vs is approximately equal to E1. So in that case, when you consider Vs is approximately equal to E1, this shunt element, instead of connecting the shunt element here, we can connect the shunt element here. The shunt element can be connected here. Okay. Now across the source, we are connecting the shunt element in parallel. So if you keep this shunt element in parallel with this source, then what happens, you can see these complete element are in series connection, because we are moving this shunt element from this end to this end, because the voltage drop across the series element is less. Since the voltage drop across the series element is less, the voltage across the source will be approximately equal to the voltage across this shunt element. Since both are same, what we are doing, we are moving this shunt element to the parallel to the source. Once you are making this shunt element parallel to the source, this series element, that is primary side copper loss and the secondary side copper loss, which are defined by this series RL element, both will become series. If both will become series, you can just all these together. Okay, so if you are adding all these together, then the complete circuit you can redraw it. Just a minute. The complete circuit you can redraw it in such a way, this shunt element comes in parallel to the source. Okay, so the complete circuit can be drawn like this. The complete circuit can be drawn like this. The shunt element has come here and your load is here. Okay, the parameters I am not labeling it. So but here you are having R1, here you are having X1, that is primary side, we will mention it as primary, JX primary. So here you are having R dash secondary and here X dash secondary. Now these elements are in parallel, then you can add these resistive elements separately and you can add the reactive elements separately. If you add these terms, then the complete circuit have become like this. So once the complete circuit has become like this is the modification from the exact equivalent circuit. So you can consider this as a modified equivalent circuit, modified exact equivalent circuit. Now coming to this approximate equivalent circuit, what we are going to do is we are going to remove the shunt element. Why we are, there was a shunt element which was here, there was a shunt element which was here in the modified equivalent circuit, that we are going to neglect it here. Why we are neglecting it? The current flowing through this path is nearly 2 to 5% of the rated current. So the current flowing through this path can still be further reduced, still be reduced by choosing a particular material. Okay, so the current flowing through this can be reduced further by using a appropriate magnetic core material. Then the current flowing through this will be very much minimal when compared to the rated current flowing through the path. So if the rated current is very much higher when compared to the current, that is the magnetizing current flowing through this path, what we can do is we can neglect this component. Okay, how we can do is we have to choose the material, that is the magnetic. Whenever we are talking about the material, we are having a core here. This is a magnetic core, or generally it is made up of iron or steel. So we can choose a proper material in such a way that the current drawn by this core element as lesser. Okay, or the current required to magnetize this core element as lesser. So we have to choose the material like that. So once we choose the material like that, what happens is the losses which are happening in the core material is getting reduced. So once the losses in the core material is getting reduced, obviously the IC is also getting reduced. What is IC? IC is the component which is responsible for the core loss which is going to happen in the core. So that is the current which is flowing through the path. When the current flowing through this path is reduced, then the overall current, that is the current flowing through this path, is also reduced. When the overall current path, when the overall current passing through this path is reduced, then the current ratio between the current flowing through this magnetizing part and the rated current is also going to reduce. So it is going to change. Now the thing is, the magnetizing current, the IM, is very small when compared to the rated current, when this is very small when compared to the rated current, we can neglect this component. So we can neglect this shunt component. So you will be getting only this figure which is shown already. So now this is called as the approximate equivalent circuit. Okay, in short circuit test, what you are doing is, here you are going to make this short circuit and you are going to obtain this elements. You are going to obtain this series elements in short circuit test of the transformer. Okay, so now we have added the series element. That series element can be given by RE1, and this resistance is given by RE1, and inductance, that is the reactance, is given by XE1. Okay, so from this you can draw the phasor diagram for this. So once you draw the phasor diagram for this, we have to start from the extreme. So V2 dash is the voltage that is at the extreme end. So you can consider V2 dash at the extreme end. Then there is some current which is going to flow through this path. So that current that is going to enter through this path, so that current will be lagging in nature, because we are having a inductor here. So generally we will be using a load that will be resistive in nature. You are having one inductive element, so this circuit is inductive in nature. So if the circuit is inductive in nature, the current will be lagging with respect to the voltage, and between these two there is some voltage angle. Now we have to see the voltage drop across this resistor, and we have to see the voltage drop across the voltage across the reactance. Now when you comes to the voltage drop across this resistor, so when you draw the phasor diagram for this resistor, if you draw the current here or voltage here, let's say this is the voltage across the resistor, the current will be in phase with the resistor, right? Sorry, the voltage and the current in the resistor will be in phase with each other. So the current flowing through this IN. So if it is in phase, what you can do, already we have drawn I1. So the in phase means the current can be drawn parallel to each other. So this is based on I1 into R E1. So this is the voltage across this resistor that is in phase with the current. So since both are in phase with the current, this current is here. So parallel to that we have drawn. That is for the voltage across the resistor with respect to the current. Then the voltage across the inductor, you know that it will lead the current by 90 degree. So if the current is like this, then voltage will lead the current by 90 degree. This is the voltage across the inductor. So in that case, you will be having 90 degree leading. This is the 90 degree leading. We should rotate in the anti-clockwise direction. So we got the 90 degree leading. So what is this? This is the voltage across the reactance, that is XE into I. So this is nothing but J into X into I. This J represents the 90 degree shift. Then you just add these two things. So we will be getting Vs, that is the source voltage. So source voltage is equal to sum of voltage across this load plus sum of voltage across the load, then resistor voltage drop, then the voltage across the inductor. So these three things, if you add vectorically, you will be getting the voltage across the source. This is the phasor diagram for the approximate equivalent circuit. Okay, so we have made the circuit to represent in a very simpler way in order to make our analysis simpler. Okay, this made our analysis very simpler. That's why we are making this approximate equivalent circuit. But you should understand that when we are going for this much simpler analysis, the accuracy is reduced when compared to the actual exact equivalent circuit. Okay, so till now whatever we have discussed is depends on referred to primary in the sense, till now whatever we had mentioned, so we had taken a circuit like this. Okay, we have taken a circuit like this, and we made the secondary EMF equivalent to the primary EMF. Okay, this is R1, this is JX1, this is R2 dash, this is JX2 dash. This is the load, right? So this is the shunt element. So this shunt element is RC and XM. So now here we have changed this R2 dash and we have changed this X2 dash. by making this voltage, that is E2 dash, right? So we made E1 is already there, then we made E2 dash equivalent to E1. So here we made the secondary parameters, we have made secondary parameters which are equivalent to the primary. In another way, we made secondary EMF equivalent to the primary EMF. So you can call that secondary parameters are referred to primary. So here we have done secondary parameters referred to primary. So that's why we have mentioned it as R2 dash and X2 dash. Now there is another way. So we had a transformer like this. We had a transformer like this. Then we made N2 as equivalent to N1. Okay, after that only everything started. We made number of turns on the secondary made equivalent to the number of turns on the primary. That's how we had started. Now what we can also do is we can change N1 equivalent to N2. Okay, so when we made N2 equivalent to N1, we made to change all the secondary parameters, everything we changed on the secondary parameters. Now when we want to make N1 as equivalent to N2, then what we have to do is we have to change all these parameters referred to the secondary. Why? Because here you are having N1 and here you are having N2. So we wanted to make E1 as equivalent to E2. So in order to make E1 as equivalent to E2, we have to make the number of turns on the primary side should be made equivalent to the number of turns on the secondary side. So once you are making that, we will be getting E1 dash here. So how we can obtain this E1 dash? So E1 divided by E2 is equal to A. This we have already seen. Okay, we wanted to make E2 as equivalent to E1. So E1 divided by A is equal to E2 dash. So this is considered as this is not E2 dash, this is E2. So E1 divided by A is nothing but E1 dash. So now this E1 dash is equivalent to E2. Now we got this voltage. So once we got this voltage, like the earlier case, what we need to do, the losses before and after this modification, everything should be same. So accordingly, we should change the series resistance and inductance value and the shunt element values. This also, we have to change the shunt element parameters also. Accordingly, we have to change the source voltage also. Okay, the procedure is same, but earlier we made E2 as E2 dash in order to make secondary EMF equivalent to the primary EMF. But here what we are doing is we made the primary EMF equivalent to the secondary EMF. Then once you are making it, all these parameters should be transferred according to the secondary. So when you are transferring this according to the secondary, we can call this as primary referred to the secondary. Primary terminals are referred to the secondary terminals. So in this case, we will be getting R1 dash, X1 dash. Here we will be getting R1 dash, X1 dash, here RC dash and XM dash. Okay, so that will be referred to the secondary of the terminals. So after we change the primary to primary referred to the secondary, we will be getting the elements like this. So how we got R1 divided by A square? Like to the similar manner, we can consider it here. So same power law should be there with compared to the before modification and after modification. So once you consider that, we can obtain this. RE and XE. So here in the earlier case, we had mentioned it as RE1 and XE1. Here we are representing it as RE2 and XE2. RE1 and XE1 represents that primary is secondary is referred to primary. XE2 and RE2 represents that primary is referred to secondary. Okay, so based on this, we can able to solve some problems that we will see later. So generally, whenever we focus, we always work with secondary referred to primary. Generally, we'll be working with the previous case where the secondary is referred to primary because it is easy to analyze for us. Okay, so this is about the equivalent circuit of the transformer. So from this, what we have done, we had a actual transformer which is supplied with a source, and we had a load on the secondary side. So this complete circuit is modified to an equivalent circuit in order to perform the analysis in an easier way. So the point is, any electrical device or any electrical component can be represented by its equivalent circuit. Whatever we read or whatever the circuit we see, that is based on some practical system. For that practical system, we can represent that practical system in terms of R, L, and C elements. So that's what we are doing in our actual circuit analysis. In circuit analysis, whatever the electrical equipment we are having, we are going to represent that in R, L, and C components. Other than that, we are having semiconductor devices. That is of different interest. So we are not including the semiconductor devices. Other than that, whatever the electrical circuit we have, that we can represent as simple RLC elements, then we can make the equivalent circuit in order to make the analysis simpler. Okay, just a minute. Okay, if you have any doubt in equivalent circuit, you can ask, else let me proceed further. So only one topic is pending for this particular transformer. Let me complete that also. So our fourth unit will be completed. If you have any doubt in equivalent circuit, you can ask, else let me proceed further. See, one thing I wanted to say, if you thought to record if you wanted to see the recorded videos and wanted to learn in future, it is not going to happen for the exam, because when it comes to the exam, you are going to read so many units. So if I have taken 40 lectures, you cannot go through all the 40 lecture videos when it comes to the exam. If you are not going to be attentive in the class, you are going to be the sufferer in the exam, especially if the exam is going to happen in viva manner, then you are going to suffer a lot without any doubt. Means the point is, if you wish to see the recorded videos in the later on stage, it is not going to happen, because you will be getting so many videos to see. So you cannot focus, or you cannot watch for 40 hours or 35 hours in order to appear for the examination. You are going to suffer at last. Okay, already your internals are very less. So if you are not able to focus on the class, your overall marks will be drastically reduced. So it's up to you whether you are attending the class properly or not. It's up to you. I am not even bothered about it. Okay, I am taking my classes regularly. If you are not attentive, it is your problem. So that will be reflected in your marks directly. Okay, is it clear?
Yes, sir.
Yes, sir.
So this is the last topic, open circuit test and short circuit test of a single phase transformer. Okay. So this is the actual transformer. So we have seen how we have obtained this transformer equivalent circuit from the actual transformer. So this is your equivalent circuit. In this equivalent circuit, what we are going to do, we are going to apply open circuit test and short circuit test, and we are going to find the parameters of the circuit. Okay. So this is the actual circuit you can consider. In this is the actual circuit which we are going to focus on transformer test. Okay. So sorry, in open circuit test we are going to open circuit the load terminals, and we are going to obtain the shunt element parameter that we have already discussed. So when this secondary terminals is open circuited, then the current flowing through this path is zero. If the current flowing through this path is zero, there is no voltage drop across this, then there is some current which is going to flow through this path. Okay. Now this current will be very much lesser when compared to the rated current. So this current is going to do only two purpose. One is for the magnetization part, another is for the core loss. So you have to bring the rated voltage. Then once you bring it to the rated voltage, there is going to be some current flowing through this path. So here the current flowing through this path is zero. If the current flowing through this path is zero, all the current which is flowing here, that is going to be flowing through this path. So it means that the primary current will be equal to the magnetization current. So from this we can obtain the core loss of the system, and also we can obtain this shunt element parameters from the open circuit test. Okay. So what is the circuit of the open circuit test? So here you are having a supply, then DPST switch. DPST means double pole single throw switch. Just a minute. DPST means double pole single throw switch. In double pole single throw switch, using one operation, it can be of on or off. Using one moving operation, you are going to switch on or off two switches parallelly. There is one switch on top and there is another switch on bottom. So now you are going to turn on or off two switches at the same time. So you are calling it as in a single throw. In a single throw, you are going to operate two switches. So this is the auto transformer. This auto transformer is helpful to change the voltage from 0 to maximum or rated. Okay. So this is the initial condition. This diagram shows that your transformer should be at 0 volt at initial condition. When it is connected near to the top, it means that if you are applying 230 volt here, then the voltage seen by this auto transformer output will be 0 volt, whereas the input is 230 volt. Even if the input is 230 volt, your output is 0 volt. When you are changing this is a sliding option kind. When you are changing this slide from this position to this position, then the voltage will be increased from 0 to 230. Okay. So now in open circuit test, what you are going to do, you are going to measure the voltage, you are going to measure the current, and you are going to measure the power. So this is the primary winding and this is the secondary winding. So now you have to open circuit the transformer secondary. So which can be our old secondary of the transformer? So there are two windings. One is low voltage winding and second is high voltage winding, which is same as primary, nothing different. But in terms of voltage, if the induced EMF on the primary side is 100 volt, let's say, and the induced EMF on the secondary side is 200 volt, then this is considered as low voltage and this is considered as high voltage winding. Here the N1 will be N1 will be lesser than N2. Whichever is having more number of turns, then more EMF will be induced, because EMF induced is given by N into d phi by dt, right? So now This phi is constant between the primary turn and the secondary turn. The number of turns is only going to change. If the number of turns on the primary and secondary is going to change accordingly, the EMF induced will be changing. If the induced EMF on the primary side is 100, then it is considered as a low voltage winding, and the induced EMF is induced EMF on the secondary side is 200, then it is considered as high voltage winding. So when comparing these two voltages or these two turns N1 and N2, which is having maximum number of turns, that is considered as high voltage winding. Which is having lesser number of turns, that is considered as low voltage winding. So in open circuit test of transformer, what we are going to do is we are going to open circuit the high voltage winding of the transformer. Why we wanted to open circuit the high voltage winding of the transformer is, suppose if you got this transformer and if you want to test this transformer, suppose if this transformer is 11 kilovolt bar 765 kilovolt transformer. So if you want to do the test, open circuit test, then it is sufficient for you to have only 11 kilovolt. If you want to open circuit the low voltage winding, then what happens is you have to connect the high voltage side winding on the source side. Okay, so when you want to connect the high voltage winding on the source side, then you should be having 765 kilovolt of source. So it is not possible to get 765 kilovolt everywhere. So in order to do open circuit test, it is sufficient to do the open circuit test on the low voltage winding. Here in open circuit test, we wanted to bring the primary voltage, that is the voltage which is applied by this auto transformer, to the rated voltage of that particular winding. If the rated voltage of the primary is 11 kilovolt, then you have to bring it to the 11 kilovolt value across the terminals. You have to tune the auto transformer in such a way that you will be getting 11 kilovolt here. Similarly, if you want to test this high voltage winding here instead of low voltage winding, you should be having a voltage source which is capable of supplying 765 kilovolt across this. So this 765 kilovolt is not an easy task, or it is not an easy voltage level to be handled. So in open circuit test, you have to bring it to the rated voltage. So if you want to test a transformer of 11 kilovolt by 765 kilovolt, so it is recommended always to use low voltage winding connected to the circuit, and high voltage winding should be open circuited, because if the high voltage winding should be open circuited, we don't need to have a source of 765 kilovolt. You don't need to have a source of 765 kilovolt which is having the voltage level of 765 kilovolt. So with the minimum voltage, we can test the open circuit test of the transformer. So in this, we are measuring three things. One is this voltage, another is this current, another is this power. So the voltage which we are measuring is open circuit voltage. We will bring it to the rated voltage. If it is 230 volt transformer, we will be bring it to the 230 volt. This is fixed. This voltage will be equal to the primary voltage of the transformer. Then IOC, that is the current measured by this wattmeter, that current is going to flow through this path. So since secondary current is 0, now very less amount of current will be flowing through that part. That current will be doing only the magnetization part along with the copper loss, along with the core loss component. So this current is going to make only the core loss component. Then the power which is measured in this open circuit test is going to give the power loss. That power loss is nothing but the core loss of the transformer. Okay, so these three things we are going to measure in the open circuit test of the transformer. So only thing is we are going to open circuit the high voltage winding, because if you want to open circuit the low voltage winding, then you should be having the sufficient voltage source on the source side. So high voltage need not to be available at all the locations. So it is not possible to perform the open circuit test by open circuiting the low voltage winding. You have to open circuit the high voltage winding because it is sufficient to give the lower voltage in order to perform the open circuit. I'm extremely sorry. In order to perform the open circuit test of the transformer. Okay, we will end this class now. We will be continuing the next class. Okay, you people can leave. If you have any doubt, you can ask, else we can end this meeting. I'm getting cough continuously, so if you have any doubt to ask, you can ask, else we can end